1655, and these gray dots are the spectra. And you can see that even the same source presents different kind of emissions depending on which state it is. And so this is thought to be related to the accretion geometry close to the black hole. For example, this is called the thermal state, which is where the accretion disk is dominant into the emission. And that's thought to be because here you can see this is the black hole, and these are different states of the accretion. And in this state, the disk is thought to be very, very close, come very, very close to the black hole itself, all the way to the innermost stable circular orbit, which is as it said, is the last stable orbit after which the matter just falls directly into the black hole. Right? And in this state, the disk is so close to the black hole, it becomes very, very hot, and that's why this emission, this red one, is the emission from the disk. It becomes predominant in these states. And then there's other states in which it's thought that emission is actually coming from a corona, which is a cloud of electron-dominated cloud that's also very close to the black hole, and that reflects the photons from the disk and create a high-energy emission. But this is not the only way you can look at the X-ray emission.
Why would the accretion disk ever end before the ISCO? I mean, doesn't
it depends. It depends on the accretion rate. It depends. It really depends on the accretion rate from the donator star. So it's like most of black holes are only seen in the X-ray when they go into an outburst.
But these particles instability. Right? But the instability doesn't come till the ISCO, right? We're seeing there's an instability before the ISCO.
Yes.
Yeah.
It's the instability, thermal instability that
from the corona or something.
No. From the
no. So cooling versus heating, you're balancing, and there is a state that is unstable, and you become very hot and puffed up.
But is it swallowing up the entire nearby star, or it's just a small portion that's coming in?
Little by little.
And what initiates the pulse? Is there some reason why it's not a steady state from the
reason
star?
is like you accrete in time, and then all of a sudden you reach this instability for which the disk becomes much closer to the hole, and then after a while it cools back down,
and then this whole thing starts again, and there's going to be another.
It is in cycles.
So how often does it repeat? Do you know?
It depends. It depends on the black hole. So most of black holes that have been detected in this way they're detected in the outbursts. So when they're bright in the X-ray. So when they're in
that seems
one
to be
of
about
these
a year.
states,
no, the answer is that they repeat about every 50 to 100 years.
Yeah, but the burst itself seems to be about a year long. Is that right?
A month.
Oh no, here is the energy. On the x-axis, you have the energy.
No, I say it seems to be going from 66 to 67. Or?
Yeah, no, they can last for the outburst can last for months or
okay,
for yes.
Thank you.
It really depends on their source. But there's also another way to look at black hole X-ray emission, which is timing, which is you measure the arrival time of all your photons, and you see how the emission changes with time. And what you want to find is that if there are any periodicity in your emission. And but it's not easy to look at just if you plot it against time. So the best way to look at this periodicity is to Fourier transform and look at the power density spectrum. And here what it means is that these peaks that you see, they correspond to an emission that is periodically changing. So going up and down with some frequency. And these are called quasi-periodic oscillations. So this is another way in which you can look at X-rays, and I'm going to talk more about this. And then there's even another diagnostic that is polarization. So here I'm not showing data because we don't have an X-ray polarimeter in space yet. So see, these are simulations from Shipman and Krolik. So polarization is the way you take a photon, the direction in which the electric field oscillates. That's the polarization, right? And so black holes are thought to be polarized at emission. So this is These are some simulation for the thermal state, which you can control it, and you can see like all these lines indicate the direction of the polarization of the photon. Of course, we cannot resolve the black hole if it's in a black hole binary, stellar mass black holes you cannot resolve. The EHT is thinking about resolving supermassive black holes in the center of a galaxy in Andromeda. So what you have to do is just sum all the different contributions. And this is what you get, some polarization degree. And you can see that it depends on the spin and on the mass of the black hole. So just by looking at the polarization, you can infer a lot about the black hole. So in my talk, I will talk about all three of these X-ray diagnostics. So one of it is, so what I do with X-ray polarization is I want to model the X polarization of black holes, including a QED effect, that is the vacuum birefringence. And also, I'm going to talk about this new mission that is going to look at the other parts, so spectroscopy and timing. So, as I said, we don't have an X-ray polarimeter in space, but it's coming up soon. So, IXP, it's going to be launched in a little bit more than a year. So, we're going to detect X-ray polarization from black holes. Finally, it's been long due. EXP is another mission that it's a Chinese lab mission. It's going to come out about 2022. This is a very small mission. It's flying right now in Antarctica. This cannot really look at many sources because it's just a small mission. But it's coming. So we will detect X-ray polarization from black holes. So what I work on is to try to model it properly so we can understand what we are looking at. And in particular, I want to include this effect I was talking about of vacuum birefringence. So vacuum birefringence was one of the first predictions of quantum electrodynamic. It's very old, like it was proposed in the 30s when QED wasn't even properly formulated yet. And then it was found again in the 50s, about 15 years later, in full QED by Schwinger. And what it is, in short, is that when you have a photon traveling in vacuum, its polarization is fixed, right? If there's electrical magnetic fields in the vacuum, they don't affect the polarization of the photon. In QED, the fact that you have a charged Dirac field in vacuum implies that there is so the photon can interact with electromagnetic fields through virtual positron and electron and positron pairs in the vacuum. So this is the electron. So this is an effective Lagrangian, and so here you can see the usual electromagnetic Lagrangian contribution, and this is the addition of QD, which is more than quadratic in the field. So you get that if you take a uniform field and you add a small photon field on top, what happens is that you find that in a magnetized vacuum, the index of refraction of light polarized parallel to the magnetic field and perpendicular to the magnetic field is different. So if you can imagine that you have the photon that is traveling in vacuum, that is magnetized, highly magnetized, and it's interacting with this virtual electron and positron. And if there was no field, the direction of the polarization wouldn't matter, right, for this interaction. But with the field, it's easier to excite electrons to oscillate along the field lines with respect to across the field lines.
It's similar to Faraday rotation?
It is similar to Faraday rotation, but here we are in the background. So this is virtual. It's very similar, yes, but now there's no real electron and positron electrons, but it's just with virtual pairs. And as you can see, it goes as the magnetic field squared. But this effect is very, very small. So in terms of like terrestrial magnetic fields, it's very, very hard to detect. There's people trying in Toulouse to test this effect. They are getting closer and closer, but it's hard. It's very, very hard. But there's astrophysical objects like neutron stars and black holes that have very high magnetic fields. So I added a little bit on neutron stars because people in the audience asked me yesterday to explain what I was saying about neutron stars. So
How do they try to measure it on Earth, just with the Earth?
Index of refraction.
they just try to measure. They try to measure in difference in time. There's a difference in the time, the speed of light, due to the difference in index of refraction. So they're trying to measure time lags of this order. So it's very, very, very compelling experiment, very challenging experiment.
But it's limited by the strength of the magnetic field that they can get.
Yeah,
Exactly.
yeah, absolutely. So I'm just gonna quickly talk about neutron stars because that's where the effect is the strongest. Neutron stars have magnetic fields that are billions of times whatever magnetic field you can ever achieve on Earth, right? So they're the perfect laboratory to test something like this. And this picture is a little bit confusing, but you have to imagine, so this is the polarization at the surface of the neutron star. Okay, so this is a ball of 10 kilometers in radius, and here it's hard to see, but this is the magnetic pole of the neutron star. And you have to imagine here there's a dipolar magnetic field, and the polarization lines at emission follow the local magnetic field lines. So these are just following the local magnetic field lines.
And these are spinning at maximum.
It's spinning fast, yes. Neutron stars spin up to 700 times a second, so they are quite fast. But what's happening? Maybe can I draw? So we have this star here that has this dipolar magnetic field, right? And we are here actually because there is a little bit tilted. Let me do it again. It's more like this, that picture, okay, and we are over here. Now, at surface, if you look at the lines, you find that the polarization has many directions because it's following the lines here, right? But if you go farther and farther away, here the magnetic field is all aligned in one direction. And that's why when you go over here, so this is the polarization limiting radius. So what happens with QD is that photons are emitted from the surface with certain polarization. And then what happens is that the polarization follows the magnetic field lines. It's parallel transported along the field lines. So when you get to where this effect is not strong anymore, then polarization is frozen again. But depending on the magnetic field, the radius at which this happened can be very, very far away. So here it's 76 times the radius of the star itself. So over there, the field lines are all lined up. And so what you see is that if without QED, if you sum all the polarization, what you expect is about 20% polarization degree, 20 to 30%. And with QED, it's just 100%.
So is the index of diffraction over unity or bigger than unity close to the star or the magnetron? Because you had 10 to the minus 24 for a Tesla, and now if you put 10 to the 16 Gauss or 15 Gauss.
Yes, so that it's just...
It's of all the unity.
Yes, so it's very important for magnetars. It's also important for neutron stars that have lower magnetic fields. But for magnetars it's striking. So these people in Toulouse, they've been trying for many years to measure this effect. With an X-ray polarimeter, you look at a neutron, a magnetar, which are these highly magnetized neutron stars, for about, here it says, 100 kiloseconds, like 30 hours, and you get a detection that is absolutely unambiguous of this effect.
But my problem was that QED is calculated perturbation theory, right? So when the effect is of all the unity,
it's not
perturbation,
no.
Because if the effect is of all the unity, wouldn't you?
Oh, it's
have
not.
to
It's
go
not
to higher-
perturbatively.
Oh, it's non-perturbative.
Non-perturbatively. Yeah.
All of
It's,
this, I see.
But the Lagrangian that you showed is just up to one loop, right? I mean, e to
No,
the
no,
force.
it's not calculated in perturbation theory. It's calculated.
QED doesn't exist non-perturbatively.
You just get. No, for this you can do non-perturbation, non-perturbatively calculate the Lagrangian. So the Lagrangian that you get, I can show you. Maybe we can talk a little bit more in the questions.
Yeah, but it's powers of alpha. You are expanding in powers of alpha. So I guess my point is there would be additional terms with higher powers of alpha that contribute
So
this much.
this is the Lagrangian for QD. Just do a path integral.
But that's up to alpha, right?
It's like you want
The correction alpha, and there would be an alpha squared.
So this is the So the one that I'm showing here is the one that applies to black hole, and it's an expansion of this Lagrangian for low magnetic fields. For magnetite, you have to use the other expansion, the expansion for high magnetic fields, which I'm not showing here because today I'm talking about black holes. But it's the two different expansions. This Lagrangian that is not approximated. So this Lagrangian it was found by Schwinger and without
with the one loop with one fermion with one electron loop.
no.
If you have another diagram where you could have another diagram with another loop inside there, and you
But
connect it with
that's just too
nobody.
expensive.
That's what you would need to get the exact answer. That would be an order alpha squared correction.
Yeah, I think
Can you please go to the slide that you said n parallel and n perpendicular? That was proportional to alpha, right? So that's actually, can you go to other slides?
Sure. I'm going to skip ahead to my backup slide.
Yeah,
Yeah,
you see,
this
it's actually, this is what, yes, alpha QED appear here. So if you're non-perturbative, why only the first order appear?
Because I have to look at the paper again, but I'm not an expert of quantum electrodynamics.
But somehow B over B QED squared can't be bigger than.
It can be.
It can
Only
be
for
bigger
electric
than 1
field.
over alpha.
For electric field, there is a critical field above which you have breakdown, but magnetic fields can exist for arbitrarily
Yeah,
large fields.
indeed, like the
Yeah,
QED
magnetic
is
field can be an arbitrary.
Yeah, instead like
There is no breakdown of the vacuum.
Wait, so can this number become of order 1?
Yeah, that's my
Yeah,
point. That
look.
was exactly my point. It's not.
BQD is 10 to the 13 Gauss.
And
So
magnetars have 10 to the
magnetars is 10 to the
15,
15.
10 to the
Well, then
16.
why can't we use them to measure physics beyond the standard model? Because QED doesn't explain. Cannot.
There is no breakdown of the vacuum. At the,
But QED is can't be used when this ratio is of order.
that's my
1.
point. But
So
something else.
we need the full standard model, or
What? So you should give me the answer to this question. What?
well, I'm surprised that
Maybe we can have
It's pretty
discussion later
interesting.
so I can go on.
You can go on. It's just an important point that.
it is a very important point. Yeah.
Okay. Where was I?
Can I
Yes.
ask another question? What's the mechanism that emits this polarized radiation from the surface?
It's just in the atmosphere of the neutron star. It's mainly electron scattering and all this like.
So it's fluctuating. The polarization is all.
No, it should like at emission should be parallel to the line to the magnetic field lines. Like that's why it looks like this. That's just all the magnetic field lines. So as I said, electromagnetars, there was an optical detection. So we don't have an X-ray polarimeter, but we have optical polarimeters. There was an optical detection of an isolated neutron stars that hinted on the presence of this QD effect. But with optical, one has to be careful because there's also the plasma birefringence that have an effect for those energies. So the fact that we found a very high polarization could mean the QD is having an effect, but also that the plasma birefringence is having an effect. So you have to be careful. That's why we need an X-ray polarimeter. So what about black holes? Let's go back to black holes. What's the magnetic field? Like a fundamental question here. What's the magnetic field of black holes, right? Because, so in theory, black holes, like the magnetic field in the accretion disk is very important for accretion. As I said, in order for matter to accrete on the central black hole, you need to remove angular momentum. And that's thought to be to viscosity, and the viscosity is thought to be induced by a magnetic field or by magnetic driven winds. So in order to have accretion, you need the magnetic field. And also jets are thought to be powered by magnetic field. Like you have like very close to the disk, the magnetic field works around the central engine and it extracts rotational energy from the hole, and these jets are created. So in theory, magnetic field is very important to explain all the phenomenology of black holes. So again, this is the main theory for magnetic field in black holes. For accretion in black holes, called the Shakur-Senior and Lobby-Covenant accretion disk, in which what's written here is just the viscosity is generated by turbulence and by a magnetic field. And the turbulence itself is also kind of generated by the magnetic field, and so you get it's like kind of a number for the minimum magnetic field needed for accretion in this model.
Viscosity is a function of radius.
It's function of radius, yes. It goes down its radius to the 3.5, minus 3.5, and it goes down with the mass of the black hole. And observations are not many of black hole magnetic fields, and they're kind of often model dependent. So you get very different estimates, but you can see that when you, and they're also define magnetic fields quite far from the ISCO. And so when you kind of translate those fields to the ISCO, you find similar strengths that what you find with the Shakur-Senior model. So for my calculations, I just used this strength, right, as the minimal assumption. So now I'm going to just describe a little bit the formalism I used to evolve the polarization through the magnetized vacuum. So I just depict the polarization on the Poincare sphere. So the polarization states are mapped on the surface of this sphere. And what it means that if the polarization is pointing up, it's circular polarization. If the polarization is pointing on the plane, it's linear polarization, and it's described with this S vector. Then if you describe it in this way, you can calculate the evolution of the polarization with this equation, where x3 is the direction of propagation of the photon, and omega is the Birefringence vector, and t is the dichroic vector. There is no absorption of X-ray photons in this case because there's no creation of real electron and positron pairs, so t is 0, and the Birefringence vector is just given by that difference in index of refraction times the wave number of the photon. So it depends on B, but it also depends on the energy of the photon. That's why in the X-ray the effect is more important than in the visible, right? Because it goes up with the energy of the photon. So if you integrate numerically this equation, Heil and Shaviv found that this effect is important as long as this quantity is about greater than a half.
What are the units?
There's all CGS units, but this is omega is 1 over length, so you get that is this is like a unit less, it's 0.5 dimensionless. It's because so this x3 is the direction of propagation of the photons, as I said. So from this, you can see that this effect, the strength of these effects, of course, depends on the magnetic field strength, but also on how long photons travel inside the magnetized vacuum, right? Because of these terms. And that's why when people say, "Oh, black holes have 10 to the 8 Gauss magnetic fields," is not enough for vacuum birefringence to be important. Actually, it is, because black holes are much bigger than neutron stars. So, and
sorry, could you just remind us what B sub QED?
BQD is 10 to the 13 Gauss, about 10 to the 13 Gauss.
And what's special about that?
It's
equivalent to the electric field.
Yeah, it's like the critical field.
The critical field for per production. 10 to the 12 volts per centimeter.
Yeah, it's when the cyclotron frequency is MC squared, basically.
Yeah. So another thing that I need to do my calculations of the evolution of the polarization is the structure of the magnetic.
But excuse me, X-ray it has some units of the
Length,
length,
yes.
right? But not the time. But you just said that when you go very much, further away from the black hole, they're very much smooth, right? So I wonder whether this derivative would be as small or not, because then they're just very uniform. But then maybe then the inverse is important, right? I'm just trying because you just said that they're all aligned, right? So there is not too much fluctuation. So then the
But
inverse
this is
would
for
be
Newton's
important.
science. This is just like what he's saying is like if you can write it in like an approximate way is that omega times delta r has to be greater than a half, right? And that tells you what's the delta r over which this effect is strong. Right, for a magnetar, this radius is called the polarization limiting radius, and it's about 76 times the radius of the magnetar itself. Right, that's just all there is there. It just tells you like over which length scale this effect is strong. Okay. So as I was saying, you need a structure for the magnetic field as well to evolve the polarization to the magnetized work, and that's another thing that we don't know. So there was recently a paper, and some people here was involved with the EHD, that they resolved the magnetic field structure that was partially organized close to the black hole at the center of our galaxy. So that's kind of like the only hint about the structure of the magnetic field that we have. This is a magnetohydrodynamic simulation that shows these are all the field lines, and this is the disk of the accretion disk. And you can see that they kind of predict the same thing, kind of like partially organized magnetic field. So not magnetic field that is organized at some length scale, which you could expect that to be true because the magnetic fields tend to be organized, wants to be organized, but at the same time, the differential rotation in the disk messes up big structures. So we will find some length scale over the magnetic field wins this struggle. And that's what I assumed. So I divided my accretion disk in regions of uniform direction for the magnetic field. The strength goes down following the Shakura-Tsuniaev model, but the direction I just divided arbitrarily.
What is RG? Sorry. It's X over RG is your scale. What is R sub G?
That's the gravitational radius.
Which is what?
It's GM over C squared.
No, for, in units, say, you're applying it to the black hole at the center of the galaxy.
It's like 10 to the 6 centimeters.
10 to the 12 centimeters.
Oh yeah, no. Sorry,
Right,
that's Newton's stat, so I'm getting confused.
Could you say it again? 10 to
10 to
the...
the 12 centimeter, about a tenth of the Earth-Sun separation. Okay. 10 to the 12 centimeters.
10 to the 6 is 10 kilometers. That's for Newton's stat.
Sagittarius star.
Sagittarius star. That's the Schwarzschild radius. Yes.
Right.
10 million miles.
Well, for stellar mass black hole is much less than that.
Yeah,
So it goes down with the mass.
We're talking about...
Well, no, here I'm talking about Sagittarius A star, but like what I'm talking about, it actually scales with the mass. Like it doesn't scale with the mass, it's just the same effect. It doesn't matter with the mass of the black hole. The mass of the black hole it kind of like falls away from the equations.
So, and you're saying that the magnetic field is going to be the same also?
The magnetic field is weaker around more massive black holes, but the length scale is much bigger. And so the two effects cancel it out.
So why do this like these magnetic field lines that go up from the accretion disk and then come back down? Wouldn't it be energetically favorable for those two just?
They do. This is just a snapshot. So it's continuous. It
it's
evolves.
just like the surface of the sun. On the surface of the sun, you have these loops. It's the
and then they get destroyed, and then you have reconnection happening, and then again you get. So it's a chaotic.
It's somehow
system.
far from equilibrium.
Like what do you mean?
Well, the minimum energy configuration would look sort of where all the magnetic fields are just going straight.
I know, but
There's
there's turbulence and there's the differential rotation in the disk that is messing up the structure. That's what I mean, that you always find a kind of landscape in which those two in completion that kind of define some structure, but those structures are continually destroyed. So what I did is that I took a photon coming out very close to the ISCO, coming out of the disk, and traveling into the magnetosphere of the black hole very close to the disk, so on the plane. And so what you do is that I divided all these sections, and in each section the polarization rotates around omega of this angle that you have to calculate in Kerr metric, but where you can see it depends on the energy of the photon, and this B is the angular momentum of the photon. Okay? And this is my result. So what I did is I took the 68 photons, which they all had the same initial polarization, right? They all are emitted. So this is the Poincare sphere as well. So all these dots indicate a polarization state for our photons. And this dark blue dot here is the initial polarization for all the photons. So if QED was not there, the final polarization would still be that blue dot, right? Because we're having these photons traveling just in magnetized vacuum. And the other dots are the final polarization of these photons for 3 different energies of the photon, 3, 5, and 8 keV, and for different angular momenta of the photons. So the yellow dots are photons that are emitted with 0 angular momentum, so straight out. The violet dots are photons that are blue shifted, so they are emitted along with the rotation of the disk. And the copper dots are red shifted, so they're emitted against the rotation of the disk. And you can see that QD has an effect first, and has an effect that depends on the energy of the photon and on the angular momentum of the photon. Right? The energy is obvious. We saw that the energy goes into our calculation, and why there's this difference between different angular momenta, it's for 2 reasons. So one reason is that red-shifted photons are emitted, so these are observed energies. So these red-shifted photons were emitted at a higher energy. So the QED has a stronger effect on them. But also, red-shifted photons travel for longer inside the strong magnetized vacuum. And so that's why you get this effect. So here, maybe it's easier to see. This time I ran 6,000 photons. Oh yeah, and the angular momentum here was of the disk, of the hole, was 84% the critical. The spin of the hole was 84% the critical spin. Now again, they're the same here. Again, all of the photons are emitted with the same polarization. So if you sum them all up, you should get a polarization degree of 100%. But you can see that as you go higher in energy, when you sum them all up at the end, what this chaotic field creates is a depolarization. You get less polarization going up in energy for the 3 different angular momenta of the photons. And here I have different spins of the hole. So this is 99% critical spin, this purple one, and then 90%, 70%, and 50%.
I'm sorry, you said this is all the same angular momentum of the star, but you're saying the different angular momentum.
These are different angular momentums of the photons.
Meaning what? That it could be 1.
Depends on where they're emitted, like in which way they're emitted from the disk. The angular momentum of the photon at emission.
But how do you measure it on Earth?
You don't measure it on Earth.
Okay. Right.
The idea is that, for example, some emission, like for example the iron line emission, gets blue shifted or red shifted depending on the angular momentum of the photon. And so you could in principle, you can divide some of like the angular momentum of the photons if you could understand where they're coming from. So there are ways where you can distinguish which is the angular momentum of the photon just by looking at red shift and blue shift. And also there's the different spins of the black hole on the right. So here are different spin, angular momentum of the photons, here are different spins. And also like this dashed line is a different configuration in the field. So like the directions are always random, I change it for each photon, but I also the size of, here I change the size of these regions in which the magnetic field is pointing in one direction. So this was assuming all of the photons at emission had the same polarization, but which is not true, okay? So for example, I showed you this simulation before, and you can see that emission, they do not hold the same polarization, so you always have to add it up. So now I took some spectra from polarization that you expect without QED, and this is the red line here and the green line here for two different spins of the hole, 99% and 95%. And on top of it, I have the ones with QED on, so the yellow and the blue. And here I'm just pointing out how important it is to include the QED effect, because otherwise you will misunderstand what you're looking at, right? Because, for example, here, let's say these are dots, these are simulated detection with EXTP, which is one of the polar emitters. And if you detected these 4 points here, and you didn't include QED, you would think that the hole was rotating more at 95%. But with QED, this is actually the 99% line. So, my point here is, of course, this is very preliminary, and I have to do much more work on it. But in order to understand what we're looking at, we need to include this effect. And here, instead, I'm using different magnetic field strengths. So these are the same, but here QED on and QED off. And here, this is QED on with the magnetic field that is 2.5 times what I was using before. And you can see that the fact is quite important. So this, of course, this is, as I said before, this is adding a level of complication on something that is already very complicated. So it's unfortunate, but maybe if we can model it well, we can learn something about the strength of the magnetic field, the structure of the magnetic field, and which is something that I would really like to understand. So, as I said, these are all preliminary. I was only calculating things coming along the disk, photons coming along the disk, so we would count for things that are looked at edge on. Systems that are looked edge on, like GRS 1915, I think the inclination angle is actually more like 75%, so it's almost edge on, but not completely. So the next step that I'm going to do next is calculating as the photons go out of the field and travel into the magnetosphere outside, which is more challenging because the parametric is more complicated, and also because you need a more complicated structure of the magnetic field, because you expect the magnetic field out of the disk to be more ordered. You can also see it here, right? As the photon travels out, it can encounter some magnetic field structures that are more ordered. And so the effect of QED could be actually the opposite. That's what I just found. Not a depolarization, but an increase in polarization, the same as with magnetars, right? Because as the photons travels through it, it sees all these lines kind of like getting more and more organized, and then you can have an increase. So this is all very open yet. My whole point here is that these polarization emissions are coming up, so we have to model these things properly. And we can learn a lot. We can learn about the spin, we can learn about the inclination of the hole, we can learn about maybe something about the magnetic field strength. So I'm almost out of time, and I still have the second part of my talk. If you have any questions about this first part before I move forward? Okay, so the second part, I just wanted to put that there as well, because it's an exciting new mission that I'm involved with. It's called Colibri, and it's this Canadian Space Agency funded it for a concept study, and it started a couple of months ago. And almost all the universities in Canada are involved, and industry partners. So these are the main people, the science team leaders. So there's Jeremy Hyde, who's the PI, QBC. I'm the project scientist for the mission. Kelsey Hoffman at Bishops is the project manager. And then we have Darrell Adbert at McGill, who is the mission planning lead. And then the two main interests that we have, the science interests, are black holes and neutron stars. And so Sarah is leading the black holes working group, and Samar Safi Harb is leading the neutron stars working group.
It's very impressive that out of 6, 5 are women.
Yes, indeed. We didn't shoot for it. It's just it happened, right? And they were actually the more engaged, and why not? It's yeah. I didn't notice before. Okay. So for those that are a little bit into X-ray mission, I'm going to summarize the goal requirements for the mission. The energy range is between 0.5 and 10 keV for X-rays. Energy resolution is that how well you can measure the energy of a photon, right? So if you're going to measure a photon at 2 keV, the error is going to be less than 1 eV, so less than 1 in 1,000. So it's an incredible energy resolution. Count rates up to 10 kilohertz, so we want to be able to measure up to 10,000 photons per second, which is a challenge for an X-ray mission. Timing resolution, so again, measuring the time of arrival of the photons with an error that is less than a microsecond. And we have an effective area, which tells you about the sensitivity of your the mission, which is about 2,000 centimeters. And as I said, we want these requirements to study accretion flows around black holes and structure of the space-time near black holes, but also neutron stars. So what are the masses and radii of neutron stars, and again, accreting neutron stars, studying the accretion flow around neutron stars. The optics are the same as NICER. So these are like collectors. It's not your usual idea of a telescope with a big mirror. Here you have many collectors that focus on many different detectors on the focal plane. And that's why we can look at very bright sources, because if we're looking at point sources and all the photons that are coming from those sources are not going to go all on the same detectors, but they're going to be spread on many detectors. And that's why you don't get the problems of pile up that you can have with Athena and other telescopes, so that when you have two photons coming one after the other, then your measure is lost. We don't have that problem because you have this big, you cannot do imaging here. You cannot take a picture. Your PSF is spread over the focal plane. But we don't care about taking pictures because our sources are point sources. We don't want to resolve our sources. And indeed, the other big mission that is coming out in Europe is Athena. And here is the effective area of Athena, this blue one. And this is Colibri, the green one. So Athena will have a much higher effective area, which means it's going to be sensitive for dim sources. But this is the effective area of Athena, this red one, at 100 millicrab, so for bright sources. For bright sources, the effective area goes down dramatically because of piling up of photons. So you get two photons, one after the others, those photons are lost. So with Colibri, we can look at bright sources. So in that sense, we're going to be complementary to Athena. Athena is going to take images. We are going to focus everything on the spectral and timing resolution. And how are we going to achieve this incredible spectral and timing resolution? It's thanks to the transition edge sensors. So transition edge sensors are incredible detectors. Everyone is very excited about them. They're very complicated though, so they're very hard to build. But the principle is very simple. You have an absorber, so some material that can absorb X-ray photons. When an X-ray photon arrives, that material heats up. And it's in thermal contact with a superconductor. So a superconductor is a material that has almost no resistance. But this superconductor is kept right below the transition temperature, the critical temperature. So the superconductor is below at a certain temperature, and if you go above that temperature, they become normal. So what you get is when the X-ray photons arrive and heats up the absorber, it heats up the superconductor as well, and so the superconductor becomes normal. And the resistance shoots up very, very quickly. And that's why we can measure the time of arrival of the photons with such big precision, because you can see like it's almost immediate, the rise of the resistance. And just by looking at the shape of how the resistance goes back to the previous value, you can also get a measure, very precise measure of the energy of the photon. So this is what you're going to see, this is what you're going to use, and this is their performance. These things are already done at NIST in Boulder, Colorado. So for those who are not very familiar with spectral resolution, but like in X-ray, so usually if you have a line like this, so this is an emission line, so there's some element that is fluorescent, and so it's emitting at a certain specific energy. And here it's emitting at two energies actually. So what you usually get when you have two lines so close is that you just get a one big broad line, because you don't have the energy resolution to see them. But here, like, you can map them very, very, very well with these detectors. And again, the time error for these ones built at NIST is 275 nanoseconds. So these are amazing, and I'm definitely out of time, but I'm just going to show you very quickly what you can do with such a thing. Quickly with neutron stars. So this was for so Hitomi was an X-ray mission that unfortunately didn't stay in space for very long because it spiraled out of its orbit and crashed, and we don't know where it is. But it was able to measure a line on the surface of a neutron star. And maybe you're not very familiar with this, but when we first got a spectra of the neutron stars, everyone was very excited, because if you get lines in the spectrum, you can get a lot of information about the star. You can get its surface gravity, you can get its composition, you can get its rotation velocity. But neutron star spectra are smooth as a billiard ball. They're completely boring. But in the X-ray, there's still some hope to detect some lines. And Hitomi found the hint of a line on an isolated neutron star, actually inside of supernova remnant. And so that's what Hitomi could do. And if Colibri could look at the same star, and this line was really there, so this is Hitomi again, this is what Colibri could do. So that's what you can do with that incredible energy resolution. You could resolve the line very well. And these are different speeds of the material. All right, so it's 0, 50 kilometers per second, and 100 kilometers per second. So you could get, from this you can get a measure of the radius of the neutron star and of the surface gravity of the neutron star. So measure the mass radius relation, which is something that everyone is really very hard trying to get. And black holes, again, I don't have much time, I'm just gonna, so at the very beginning, 5 minutes, at the very beginning of the talk, I showed you all these power density spectra. So we detect some oscillation in the X-ray emission of black holes. And if you have a very good timing resolution, you can look at these oscillations and try to understand. So like there's many theories on why we see these oscillations. One theory, for example, is that you have the accretion disk, that is this gray, and then the black hole spin is misaligned with the accretion disk. And then the very, very inner flow close to the disk precesses, so it tends to rotate around the spin axis of the hole and not the spin axis of the accretion disk. And then it kind of gets warped and precesses, and that's why you see this emission that is going up and down with the precession of this flow. But there's other theories. We also see those are like about once a second, but we also see hundreds of times a second QPOs, high frequency QPOs. And so all of these frequencies are thought to be related with some oscillation into the accretion disk, right? And since the Kerr metric is completely determined by the mass and the spin of the hole, once you have those two elements, you can predict exactly what these frequencies are. And so this is the idea. For example, here you have it's a simulation for a future mission. But you have this line is for 7.1 solar masses and 60% spinning black hole, and this is for the same solar mass but 70%.
So this frequency has something to do with the precision of the disk of the rotation disk of black hole, or?
So like for high frequency, so for low frequency, they think about this lens stirring precession very close to the hole. For the high frequency QPOs, you have all this. So how they calculate it is like if you have something that it's perturbed, some perturbation, right? So you perturb something radially, what's the oscillation frequency? If you perturb something vertically, what's the oscillation frequency in the Kerr metric, right? And that's what you find. So with Colibri, you can measure these frequencies. And so we simulated how well you can constrain the mass and the spin of the black hole, assuming it's Kerr. And here this was for a 10 solar masses black hole, spinning at 95%, and you get 9.92 plus or minus 0.047, so quite good, and 0.95 plus or minus 0.001. So that's pretty good, and you can even constrain the Kerr metric itself, because what you can do is that you can perturb the metric. For example, having a charge on the hole, which we know it's not going to be there, but the charge changes your metric. And so you can say, if I detect these oscillations, how well can I constrain the charge to be 0? Right, that's something that you can do as well. So, okay, I see that I'm really out of time, so I'm going to stop here. Thank you very much for following through all these different things. And thank you very much for your attention.
Do you have questions?
So, can you also tell us something about the disk? Because the precision could come from the disk, right? I mean, if you have a rotating black hole, right, and then there is a disk over there, maybe that caused this precision. So, why can't you just measure something about the disk property?
Yeah, that's something that the idea that I'm trying to convey here is that to get the most out of the X-ray emission from black holes, you have to model all these different things together, right? And if you model them together, you can better constrain all the different properties, right? So you want to do it together. That's what I want to do.
It's just the properties of your black hole, like A and M. Or
Yes.
not the disk.
No, like these frequencies are thought to be, as I said, just some perturbation frequencies, and those are totally determined. Like if the metric is squared, they're totally determined.
But they are like radius dependent.
They're
or
radius
se-
dependent.
Several
Indeed, like
different
what
kind
you
of
see-
characteristic frequencies. that
What you
could
see
be
here
involved.
is actually, so you see this frequency drifting. So they change with time. And the reason why they think that they change with time, so this is a simulation, but that's approximately what you see. Like they change with time, but they change together. Like they're related to each other. And that's why people think that they're related to this perturbation frequencies. And the idea is that are changing as the inner radius of the disk is changing.
Okay, so it's oscillations at the inner edge.
They're in the oscillation very close to the inner edge. This high frequency QPOs, that's the main model is called the relativistic precession
Actually,
model.
it's not established.
It's not
It's just-
established.
it's just
like,
an idea,
It's just
right?
an idea, right?
I
But-
don't believe it.
But you know, being a student of Marek, I have to
You
be
have
a
to
big
take
fan
it
of this
seriously.
particular one. Because this
So
is
yeah, I have to like
So I
point
think, you
out.
know, when you say that you'll measure the spin 2.047,
If this is true,
if the model is correct and, you know, it's
so
sort of-
like if the idea is like we're gonna measure it so much better that we can also see like maybe determine if the model is correct or not,
Okay,
right?
yes.
So like here, so I was going very fast. I should have mentioned like this is just a model for it, and if that model is true, you can constrain it very well. But you can constrain it as well with polarization. You can constrain it with continuing fitting models, and if you can put all these different things together, you can understand where you're doing something wrong, other than fitting for the quantities themselves. That was the entire idea of my talk. Like you want to do all these things together.
So this fixed ratio, I get where is the particular frequency coming from, but where is the fixed ratio?
So this frequency is like difficult. So one is so this fixed ratio between these two. So the highest one is the orbital frequency, just simply orbital frequency around the hole, and the second one is the radial epicyclic frequency. So how it goes up and down, and the two. But those two. So what you're measuring here is the ratio of the radial to this one.
Nice.
Right? That's why they go together, because this is actually what you're actually measuring is the ratio of one frequency with respect to the other.
Why should it be 3:2?
I don't know.
Right? Isn't that the big mystery? Why should it be 3:2?
No.
In this model, it's not obvious.
I know. Like actually, this model, like this model is in contradiction with the other model. For example, like this is saying, oh, there's this precession that go around, and the other one is really something in the disk that is oscillating. So it's not clear what is causing these oscillations at all. But the idea is like with better telescopes, maybe we could figure it out.
Yeah, that's exactly the expectation of the community of people interested in QPOs, that future observations will help a lot with figuring things out.
Yeah.
Okay, any more questions? Okay, then let's thank the speaker again. And you are welcome to join us at 6 p.m. For dinner if you're interested. We have 3 places to join.
Yeah, I'll send you something.